Okay, in this video we're going to take a look at the parallel axis theorem. I've mentioned it a couple of times as we were doing the calculus method for determining moments of inertia. And the parallel axis theorem, it's basically just a practical way of determining a moment of inertia if, and this is the big if you know what the moment of inertia is through the center of mass. So the parallel axis theorem, it has some practical applications. For example, if you look at a bicycle wheel, then you'll know that the bicycle has many spokes on it. And let's just say you want to determine what is the moment of inertia for that wheel. Well, you know that the moment of inertia is going to be the sum of all the individual moments of inertia. So for example, you have the ring, that would be mr squared, and we're rotating around this center point, so we have the ring, but then you have these long thin rods. And we know that ICM for a long thin rod is 1/12 ml squared. Now, what if you forget how to do the calculus method? It's like, well, gee, I just looked up 1/12 ml squared. What do I do about the moment of inertia for this? And so, it's going to be the sum of all of these, but you've got to change the moment of inertia from 1/12 ml squared to something else. And in this case, we could say it's close enough just to say that it's going to be 1/3 ml squared. But how do you get that 1/3 ml squared if you're not using calculus? What if you go beyond? For example, if you look at some wheels, they'll have an outer radius where the tire is, then they'll have a large hub in the middle. The axis of rotation is dead center, so right here is going to be the axis of rotation. So you basically have a fairly solid, fairly thick tire, right? And then you've got, a couple of spokes here. All right, so those spokes no longer extend all the way to the axis of rotation. So again, you got to find some method for doing it. And if you don't remember, or maybe you're not sure how to use the calculus method, you've got to do something. Okay, so the parallel axis theorem, it's actually very quick, it's very straightforward, and it's a very practical way to come up with this new moment of inertia. All right, so by definition, the parallel axis theorem is equal to, all right, so we have I. This is, sometimes I label it as I nu just so you don't get confused, but I nu is equal to I through the center of mass plus m times d squared. All right, so we're looking at the mass of the object for which we're trying to find the new moment of inertia. So that's what this m stands for. And this d, this represents the distance that you had to move the axis of rotation. So if we look at the long thin rod example, like I've kind of set up for the bicycle wheel, we know that the axis of rotation through the center mass is going to be right here. And that means this rod, if it were like a spinner or something like that, it would go down on this side and swing up on that side if I were to try to spin it. So I know that the moment of inertia is 1/12 ml squared for that. But I want to know what it is for the end. So you shift the axis parallel all the way to the end, and d is the distance between these 2 points. Now, it's called the parallel axis theorem because the axes must stay parallel to each other, so that here the axis is of rotation is coming out of your screen towards you. It's perpendicular to your screen, and it stays perpendicularly oriented to the screen all the way out to the edge, such that these two axes are parallel. Okay, so when the axis is here, it still swings down in this direction, but there would be no rotation of the top side at that point, of course, because it is it's fixed. The top can't move, right? That's the point that doesn't move. So what is the new moment of inertia for this. So we know it should come out to be 1/3 ml squared. So now let's demonstrate that. So we have I is equal to ICM, which is 1/12 ml squared, plus m times d squared. And d, now the whole length of this thing is L, remember? As we go from here to here, the entire length is L. So d, in terms of the geometry of this, becomes 1/2 L, and the quantity is squared. So we get I is equal to 1/12 ml squared plus m times 1/4 L squared. So this is where we just have to be careful with our fractions. And 1/4 is going to be 3/12. So we get 1/12 ml squared plus 3/12 ml squared, which is equal to 4/12 ml squared, or the 1/3 ml squared that we were expecting. So this tends to be a preferred method because it's just that much easier than trying to set up the calculus, especially if you're not particularly comfortable doing the calculus. Now, what if we had the case where the axis of rotation extended somewhere beyond? Okay, well, if it's going to be somewhere beyond, then it's D is just going to go from this point all the way out here to this point. So we would just have to extend that arrow, so to speak. And you could put it in terms of the length, so maybe this is 1/2 L here, and maybe this is 1/4 L. So basically you could say that we got 3/4 L for D. Okay, and if that were the case, then you would set up I is equal to ICM plus MD squared, or 1/12 ml squared plus m times, and what did we say this would be? 1/2 plus 1/4 is 3/4 L squared, and then you just take it from there. I'm not going to solve this out in its entirety, but what ends up happening is that the further away you get your axis of rotation, the more significant this MD squared term becomes, and the more insignificant the ICM term becomes. So that effectively what ends up happening is when the axis of rotation gets far away from the edge of the body, you end up with what is effectively a point particle. Okay, so that's the parallel axis theorem without proof. It's just demonstrated for you. What I'm going to do in the next video is actually prove that the parallel axis theorem is ICM plus MD squared.